Okay, welcome back everyone. In this video we're going to quickly go through some of the key points for Unit 5 on unbalanced forces, and we're going to start by looking at some of the conclusions that we made from our first lab on forces acting on a system. And we noticed that there were two things that affected the acceleration of the system. First of all, we noticed that as we increased the net force, that the acceleration increased as well. So A is proportional to the net force. We also saw that as the mass of the system increased, the acceleration decreased. That was an inverse relationship, so the acceleration is proportional to 1 over the mass total. Putting these two things together, we come up with A is equal to F net over m total, or bringing m total to the other side, we have F net equals mass total times acceleration. And that is Newton's second law. So a couple things that I want to point out about this very important equation. First of all, notice that I put little vector symbols on F and A. Okay, so this is a vector equation. So F net and A are vectors, which means that if I know which direction the net force points, that's also going to be the direction of the acceleration. So that's very important. We also want to keep in mind that this equation is really telling us about the causes of motion, the forces that are making things move, versus the effects of those forces. So the left side of F net equals ma are all the causes, the things that make things move or not, and the right side are the effects, or the acceleration. Okay? Now last unit we saw that if the forces were balanced, if F net was equal to 0, then the acceleration was also 0. And that was a special case of Newton's second law. Okay? Now the other thing that we want to keep in mind when using F net equals ma is that you can use it in one dimension at a time. So you can use it to analyze the net forces in the x direction. You can do it to analyze the net forces in the y direction. And we even did this when we talked about doing the net forces that were parallel to a ramp or the net forces that were perpendicular to a ramp. So there were lots of different applications. Okay. We also did an experiment where we looked at the force of friction. And we saw that there were two variables that affected how much force of friction you had. And we saw that the force of friction was equal to the coefficient of friction, mu, times the normal force. Now the normal force is something that changes on a case-by-case basis, so the best thing to do is draw a force diagram and figure out what the normal force is, and that allows you to find the force of friction. But we also said that there were two types of friction, that there were static and kinetic. And this really has to do with what's happening in the situation. Is the object at rest, but you're trying to make it move? That's static friction. Or is the object sliding or moving already? That's kinetic friction. And the two coefficients are very different. Mu static is larger than mu kinetic. Okay? It's harder to get something moving than to keep it moving. And also, the force of friction, static, has a maximum value that it can go up to. So that's why we have the less than or equal to sign, which means that if I graph the force of friction versus the force that I apply to an object, I can push very lightly on this board. There's actually a glass board right in front of me that I'm writing on, and I push it very lightly and it's not going to go anywhere. I keep pushing harder and harder, and there's going to be more and more static friction until I eventually reach this value, the coefficient of friction times the normal force. And this is a heavy board, so I'm not going to reach that today. but that means that it goes up for a while until it reaches this maximum value of mu s times the normal force. After that, it's going to drop back down, and this will be mu kinetic times the normal force. So the force of friction kinetic is equal to mu k times the normal force, and that's always true. So no matter how hard you push on something, it will have a constant force of kinetic friction. That means that the harder you push, it's going to accelerate more because of your applied force, but the amount of kinetic friction will be the same. Okay, so let's also remember that the force of friction is parallel to a surface in this equation, and the normal force is perpendicular to the surface. So let's just keep that in mind. Okay, now we'll wrap up by talking about a couple of applications, and the most common application that we see and sort of think about a lot are hills or inclined planes. And we did a lot of this back in Unit 4 with balanced forces, so the idea is exactly the same, okay? That if we have an object here, we could have the force of gravity going straight down, we could have a normal force, and then, depending on the situation, we could have a frictional force. So let's say that an object is sliding down the inclined plane, then we could have some type of a force of friction pointing up. Okay. Then what we would do is we would say that if I have an angle of theta right here, that I could draw components for the force of gravity. And the force of gravity would be the hypotenuse, and my angle theta would come back up to here, and this would be Fg cosine theta for this side, and this side would be Fg sine theta. And again, we talked about that in the balanced forces video as well. Okay, now the last thing that we will talk about is what happens when you have more than one thing in a system. That's what we call the multiple object system. And we saw this in Mastering Physics, where we had 3 blocks connected and you had to find the tension in between those 2 blocks. We saw it in the F equals ma lab, where we had a block sitting on the table and a pulley and a hanging block. So we saw this in a lot of different scenarios. Without going through the gory details, when you have multiple objects, you have 2 things that you can do. You can apply Fnet equals ma for the entire system. Okay? So in other words, you can isolate the entire system, and that means that forces that are inside of the system, such as this tension between the blocks, don't show up in the net force. Only forces that act on the system as a whole. And you can do that for the pulley. We even had a problem in one of the worksheets where we had a Atwood's pulley looking like this. Okay? If you can figure out the net force acting on the entire system, you don't need to dig into the details. However, you can also write for each object within the system, you can write Fnet is equal to ma. And you can write this as many times as there are objects in the system. And sometimes if you're on an angle, you might have 2 dimensions per object. So potentially you could have many different Fnet equals ma equations, but they all work the same way, that on the left side we put the forces, and on the right side we look at their effect. So the moral of the story is that you need to decide whether you're trying to find a force or something that is internal to the system. Then you have to break things up and look at each object. Or if you're just looking at the total acceleration, you can look at the system as a whole. So I hope that this has been helpful, and make sure to let me or Ms. Habert know if you have any questions. Thanks, and we'll see you next time.